Hey there, welcome back to the channel. Today we're going to build this circuit with this microcontroller and then write code for it to get temperature from this sensor. Let's get to it. If you recall from the last episode, we're going to build this voltage divider. I've drawn a Fritzing diagram here to help us out. This is our 3.3 volts comes across this net, down this wire, and here's our R1. This is our 330 ohm resistor. This does not have a component for our sensor, and I didn't feel like making one, so we just used a variable potentiometer here. But then the resistor comes through here, or the voltage comes through here. Then we have, this is our R2, travels back down to ground. Then right here, we're tapped off of the spot between R1 and R2, and that comes back, and this is our V out of the voltage divider that comes into our analog input. Let's go wire this up. And here it is physically. We've got our 3.3 comes up to this rail, over, down to this leg of the resistor, comes out here into the sensor, back from the sensor here to ground. And that ground you can see is tied back to ground on the board here. And then this green wire we've tapped off between the sensor and this resistor, and it comes back to the analog input here. Alright, now let's go write some code for this. I put together a real simple app. This is not going to be what we actually end up with, but this is a good test. Just defined our reference voltage and then this 330 ohm resistor here. And then I have a simple app that starts up. We create an analog input port, so reading at A0. Then we read that A to D, so we read the voltage directly. We calculate our resistance using that resistance formula we talked about before. This comes from that best fit line for the GM sensor that we calculated in Excel. And then it waits 5 seconds, goes back and does it again. And it just outputs some messages to the output. So let's take a look at what that looks like when it's running. You can see we're getting about 2.85 volts, 2080-ish ohms of resistance. Now it's interesting that it says we've got 105 degrees, 106 degrees. It's at room temperature right now, so it's probably 67 degrees here in my office. So we know that that's wrong. First thing we have to ask ourselves is, why is it wrong? Is that a reasonable thing to be wrong on? Recall when we first profiled this with the ohm meter, it was near infinite resistance at room temperature, or it was infinite resistance. So I would have expected an even higher resistance than this. Let's go take a look at the math real quick. Here I plotted the data that we had, and then I extrapolated. So extrapolation means adding data that is outside of the bounds of your data set. We had up to 650 ohms. I ran this all the way out to 3,000 ohms. And if you look at this curve, based on that best fit line, it actually levels out really a lot. So I would say that outside of about 650 or 700, so outside of this part of the curve up here, it is probably invalid. If we say the resistance is greater than 700 ohms maybe, we will ignore the temperature and just say it's not a valid temperature. So that explains what we're seeing there. Now let's plug in the kettle, drop the sensor in, and turn it on and see if this temperature looks like what we're expecting. Remember, this thing has a lot of inertia, so it heats up really fast. So even after I shut it off, this keeps climbing. So our temperatures might not be exact on the way up as they are on the way down. Right now we're reading 158 on the thermometer, and our code says 169. Our code works, our circuit works. The curve just needs to be calculated and redone a little bit more. Now that we actually have a sensor hooked up to the microcontroller, we can re-profile it and get those values that match this exact microcontroller and sensor and get a much more accurate curve. After I finish recording, I'll re-profile this, come up with a new curve. The important part here is we're just making sure that the code is giving us a sensible result. I've reprofiled the sensor, came up with a new equation, which is much, much better. I then refactored this code so that it's a lot simpler to use. You can see now we just have a coolant temp sensor, and you tell it what the resistance is and what the curve is, information like that. Once we have that, basically you just call sensor temperature, and it gives us our temperature back. Much less code, much easier to read. The sensor itself, you can see I've changed to a natural log function here. The implementation, if you're interested, I've got a link down in the description. There are actually links to all of this code, as well as the fritzing diagram, bill of materials, everything that we're working on so far. That's all there is to it. Thanks for watching.